Hi, this is Maysie Calzone from Maysie's Algebra Initiative, and today we are going over the Unit 9 topics from Algebra 1. First off, we have polynomials, then we'll move on to operations with polynomials, and we'll wrap it up with factoring. Let's get started. Okay, first off, what is a polynomial? A polynomial is an algebraic expression with two or more terms. Some examples include 3x plus 2, 4x squared plus 3x plus 3, and 5x cubed plus x. These are all just expressions with more than two terms, two or more. A monomial is an algebraic expression with only one term, so examples of this would be 3x, 5, and 2x squared. Okay, parts of a polynomial. What I have highlighted here in red are your coefficients, or they're just the numbers that are in front of variables. So the numbers that are in front of letters or other variables like y, z, x, a, b, all that, those are called coefficients. A number that has no variable is a constant term because it remains constant no matter what x value or what variable value you plug into it. Standard form of a polynomial. Step 1 for putting polynomial in standard form is you have to make sure that it's in descending order. And when I mean descending order, it's in descending order of the power of the variables. So it starts with the variable with the highest power, so in this case it's 2, the highest power here is 2, so the term with 3x squared goes in front. Then it's just the x, and because this constant on the end has no variable, it's just gonna go at the end. Okay, and once you do put it in standard form, the number I have here underlined in green is called your leading coefficient because it's the coefficient that leads the entire equation. Okay, and then down here, I just explained more of what decreasing order is. And here's an example of the variables listed. X cubed is greater than x squared, which is greater than x, which is greater than no variable at all. Okay, like terms. In order to write a polynomial in standard form, you must combine all like terms. Like terms have variables with the same power. So examples here could be 5x and 6x because they both have a variable with a power of 1. And then another example is x squared and 3x squared. They both have the variable x squared, so they are like terms. Non-examples are 5x and 5x squared. They do not have same power. And neither does 3x cubed and x squared, because 3 has a power of 3, 2x has a power of 1 on its x, so they do not have the same power. Do not have same power on variables. Okay. Now we're moving on to monomials, binomials, and trinomials. This is just a slide giving examples of what each are. Polynomials, binomials, and trinomials are both examples of polynomials. They're just more specifically named. Because polynomials just encompasses two or more terms. Well, binomials have just two terms, and trinomials just have three terms. So we already kind of went over monomials. So they have a single term, and here are some examples. Binomials have two terms, so 2x cubed plus 3, two terms, and 3x minus 4, two terms. And trinomials have three terms, so 5x squared plus x plus 1, those are three terms. And then 6x cubed plus 4x squared plus x. Operations with polynomials. We're going to start off with addition. And all you do in addition is add like terms. Remember when we went over like terms? See, those come in handy. So let's look here. So I have the like terms underlined in color-coded order. So I looked at my first term, 3x squared. Okay, is there anything in here that has another x squared? No. I look over to the next one here. And is there any one of these terms that has x squared? Yes. this has an x squared in it, this x squared. So I add them, and I just add the leading coefficients. And if there is no leading coefficient, you just assume it's a 1. So 3 plus 1 is equal to 4. So I'm going to have 4x squared, and you just keep the same variable. Now I'm going to look here. X. Okay, I'm looking across the equation, see if I can find any more just plain old x's. Oh, I found one. So I have 1 and 3 in its addition, so 1 plus 3 is equal to 4. I'm going to write that in. Okay, now I move on. There's no more terms here, and I've already used these two terms, so I just have the 4. And there's no other terms to add it to, no like terms that match that 4, so I just pull down the 4. Simple enough. Okay, subtraction is the same exact thing as addition, except for you have to be careful because the negative sign here distributes to each of these terms. So if before the problem you feel more comfortable, you can quickly just jot out the expanded version. Because see how all these operations switch up here? Oops, that's blue color to use. Like this positive 3x became a negative 3x, and the negative 1 became a positive 1, because that means that the negative is going to spread to it all. Okay, so down here I wrote out the longer work. 4x, I looked to find another 4x term. Okay, I mean not a 4x, but an x term with a x to a power of 1. And I did, the 3x here. So I know I have to subtract a positive 3x, or could I just added negative 3x by distributing it at first? So 4x minus 3x is equal to x, and then I look to the 3. Is there any more constants? Yes, here. So 3 minus 1, negative 1 is going to be a positive, so it's going to be 3 plus 1 is 4. And then negative 2, there's no thing that matches that, and I distributed the negative. And by the way, if you distribute like this, you just add at this point. Add if you distribute. Distribute. Down here is the work with not distributing. Up here is the work with distributing. Distribute. Okay. Multiplication using FOIL. FOIL is a method to multiply two binomials. So two terms, polynomials, that are being multiplied together. FOIL stands for first, outside, inside, last. At first this might sound a little confusing because you're like, whoa, what is first, outside, inside, last? But this is just describes the order in which you should multiply the terms. And I'll show you how you do that. Okay, here's a written out example of FOIL. And we have 3x plus 1 times x minus 2. Okay, let's go through our FOIL steps. First, F in FOIL. I take the first term of each binomial, which is 3x and x. They are the first terms in both, and I multiply them out. So 3x times x is equal to 3x squared. Then I multiply the outside terms. Outside meaning they are furthest outside. So the outside term on this would be 3x because it's the further outside. If this is like the inside line, this is the outsides. So that's outside. And then 2 is the other outside number. And I have to remember this negative here. Just gotta be careful of that. So 3x times negative 2 is negative 6x. Then I do inside, which is the two inside terms. Like I said, this would be considered the outside. This line in the middle would be the inside. So 1 and x are my inside terms. So 1 times x is just x. And then my last terms, which are the last terms in each individual binomial, which would be 1 and negative 2. So 1 times negative 2 is negative 2. I just write out all my terms side by side, and I then combine the like terms, and I end up with 3x squared minus 5x minus 2. Okay. Okay, here's one thing I also want to go over really quick. These are just, this is just a fancy way of simplifying two binomials, and it's called square of a binomial. And this can be written as a binomial, A plus B. And I can show you how this works with factoring. You can either memorize this rule, or you could just factor it on out when you see something like this. But you see how I have two binomials because it's just this one squared? The pattern is that if I have a plus b squared, all the entire thing squared, it's going to be a squared plus 2 times a times b plus b squared. But if you can't remember this rule, you can use factoring by writing out this term as this one and using the factoring method. And then here's an example using numbers more like you would see. So for factoring, you would write it out like this times this, and then factor it out. Okay. Here are some practice problems. Pause the video, solve them out, and then unpause the video when you're ready for the answers. Okay, here are the answers. We have 6x plus 4 because I combined like terms, which were 3x plus 3x is equal to 6x. 2 plus 2 is equal to 4. So that's what I ended up with. Then I went on to the subtraction problem. 5x squared has no like term, so it remains its own thing. Negative 4 has 1 as its like term, so I subtract the positive 1, so I get negative 5. And then the x has no like terms, but we have to remember there's this negative right here, so it's the negative x. So I have 5x squared minus x minus 5. Okay. Now the last one was a multiplication one, and I used the FOIL method because I had two binomials. I did first outside, inside last, so 4x times x is 4x squared. 4x times 3 is 12x. 2 times x is 2x. 2 times 3 is 6. So I listed out my terms, and then I combined 12x and 2x because they are like terms, and I ended up with 4x squared plus 14x plus 6. Okay, next up we have factoring. Factors are, first off, what is a factor? A factors are two terms that can be multiplied together to make a new term. So these can be something simple like these two constants, 3 and 2 being factors to make 6, or they can be something more complicated like x plus 1 times 2x plus 3. Those entire terms can be factors because they're multiplied together to make a new term. Okay, the goal of solving a factoring problem is to take a polynomial and simplify it into the smallest parts. Okay, and we do this by finding the greatest common factor. The greatest common factor is a term that all the polynomials have in common. It's the greatest factor that they all have in common. So let's look here. First, I'm going to look at the numbers. And I have 3 and 9. What two numbers go to 3 and 9? I can list 3 and 9, numbers that multiply to make 3, 1, and 3, and that's about it. Numbers that multiply to 9 is 1, 3, and 9. Because 3 times 3 is 9, and 1 times 9 is 9. And those are the three numbers that are factors of 9. I list out my factors like this, and I choose the largest one in that they both share. In this case, it's 3. So I know I can write a 3, and then parentheses of whatever is left. And then I look to my variables. And the first term has a single x, and the other one doesn't have any variables. So that means I cannot take an x out. I can only take a variable out if they both have it in common. So if I listed my variables, I'd have x and then like nothing, and they share nothing in common, so I can't do anything. So once I find my GCF here, which in this case it's 3, I divide each term by the GCF. So 3x divided by 3, It's just going to be x, and that's just going to be 3. And then I put the term on the outside, the GCF. And it's going to look like that. Okay, here's another example. We're going to do this. First off, I'm going to look at the numbers. We have 5 and 10. So 5, 1 times 5 is equal to 5. And because 5 is a prime number, its only factors are the number 1 and itself. Now I'm going to list the factors for 10. 1 times 10 is equal to 10, and 2 times 5 is equal to 10. Simple enough. Now what's the greatest common factor between the two? It's going to be 5. So GCF, we have 5. Now let's move on to the variables. So we have x squared and x, which is just equal to x times x, and x is equal to x. So they each have a single x, so I can take the x out. Good. Now I divide each term by the GCF. Divide by 5x. Remember, when we are dividing powers, we just subtract, so this is going to end up just being x, because the 5's cancel, and 2 minus 1 is 1, so x is the first. And we divide by 5x. That's 2, that's 1, and those cancel out, so we're just going to have plus 2, and we keep the GCF on the outside. Okay, we already talked about that. Now we're doing fancy rules factoring. These are just like rules you should know about factoring. They're patterns you can pick up to make your life easier. So if I had, this is called difference of squares. If I had a number that was the square of another number, a perfect square, and another number that was a perfect square, another number, and I was subtracting them, I could just put them into this format. A plus b times a minus b. And here's a real world example. So if I had x squared and 4. 4 is a perfect square because it's 2 squared, and x squared is just x squared. So they're 2 squares. And I can simplify that into x plus 2 and x minus 2. And if I were to use FOIL and work this out and simplify it all down, I would end up with this. So this is just something you have to memorize. So this is just a memorized thing. And it could just make your life easier when solving fractions. Okay. Now here's an example. And the only step when you identify the difference of squares, see how when I look here, I'm like, oh no, I don't have any common factors because this one has no numbers and this one has no variables. Well, I'm going to look at it and see, is y squared a perfect square? Yes, because it's just y squared, 2 y's. Is 36 a perfect square? Yes, it's 6 squared. So then I realize my terms will be y at 6. So I do y plus, I can rewrite it as y squared minus 6 squared, which kind of matches the a squared minus b squared. And I can rewrite it using the rule of difference of two squares. And I would get y plus 6 and y minus 6. Okay, here's some practice. Pause the video now to work out your problems, and then unpause the video to check your answers. Okay, so for number 1, this was an example of and this was an example of factoring. So I first started with my numbers and I listed the factors. The factors of 3 are 1 and 3 because 1 times 3 is 3. The factors of 6 are 1 and 6 because 1 times 6 is 6, and 2 and 3 because 2 times 3 is 6. The greatest they share is 3, and there's no variables in common between them. So I divided each term by 3, and I ended up with x plus 2, and then I just put a GCF on the outside, so it's going to be 3 times x plus 2. For number 2, this is another factoring problem. I listed up the factors for 4 and 2, which is 1, 4, because 1 times 4 is 4, and 2, because 2 times 2 is 4. And then for the second number, it's 2, so 1 times 2 are factors, because 1 times 2 is 2. And then I went to my variables, and I listed out my variables, and they only shared a single x in common. So I divided each term by 2x, so I ended up with 2y plus x, and then I just put those in parentheses and multiplied it by the GCF, which is 2x. For number 3, I figured out that the GCF was 2xy because there wasn't a lot of space. I just wrote out the GCF, but I'll talk you through it. We already listed the factors for 4 and 2 in number 2, so we know that the greatest one is 2. And both terms share an x and a y in common, so I can take those out into the GCF. So I divided each term by 2xy. The first term just simplifies to 1 because any number divided by itself, or any term divided by itself, is equal to 1. And then the other one, both the variables cancel out, and the 4 simplified to 2, and the 2 became 1, so I ended up with 1 plus 2. Which would be 2xy times 1 plus 2. And this variable, this is kind of a trick question because you could just simplify this to 2xy times 3, because you could have simplified the original problem into 6xy by adding them, because they are like terms. But for the sake of this exercise, that all you had to do was simplify it into this. Okay, so number 4. 3 plus y times 9 minus y squared. 9 minus y squared, if I looked at it, I realized I couldn't factor anything out. They don't have any greatest common factors, but I realized this is following the rule of difference of two squares, because 9 is a perfect square, because 3 squared is equal to 9. So I simplified it down to 3 squared minus y squared and fit it into my formula of a plus b times a minus b, which is the difference of squares rule. So I ended up with 3 plus y times 3 minus y. Okay, this last one, there's no numbers to compare, so I listed out the variables. So this is for the first term, this is for the second term. I have x and then 2 x's, because x squared is just 2 x's. And I have 1x in common, so I could take 1x. So I divide each term by x. This will just be 1. And if I have x squared divided by x, that's just 2 minus 1. So it's just be normal x. So x times 1 minus x. Thank you so much for watching. I hope you learned something new today. And this is Maysie Calzone for Maysie's Algebra Initiative signing off.